So I don't think Nathan will be showing up. I think he just kind of did a peace out, and I don't think we're going to see him again. So that's perfectly all right. I think I'm going to record this in case he decides to watch this on YouTube later. And I'm sorry if I sound a bit congested right now. Allergies are killing me right now. And if allergies kill me, you guys are both invited to my funeral, just saying. But you'll probably be the only 2 people there. I'm not all that popular. I know, hard to believe, right? So all that aside, I feel like we should just kind of start with our very first thing we covered, which is limits, and then maybe do some limits, do some derivatives, and then tomorrow we'll cover everything else from the class. So let's just kind of have a cursory review about limits. Limits are really important because that's what derivatives and integrals are both built on. They're both built on the concept of a limit. So limits can exist graphically, algebraically, and analytically. Talk about the graphical interpretation of a limit first. So a limit looks like this. X approaches some value of some particular function. So they work really, really well. Limits can be really easy or they can be really hard. So if we have a situation like this where clearly the function is continuous on the entire domain, we don't have any discontinuity, limits are easy. All we would need to do is plug in 2. And then, for example, if the y value of this point is 1, we can easily see that the limit would have a value of 1. But why is it even important to know what limits are? How are they useful? So limits are useful when we have a situation where maybe it's not continuous. Like what if we have maybe a hole in the graph? Something like this. So we can see that the function is continuous at every point except when x is equal to 2. So does that mean the function definitely does not exist? We can say that f of 2 is undefined. I'm just going to say equals u for undefined, or UND, I guess. I'll write UND for undefined. But then what about the limit? So that doesn't necessarily mean the limit doesn't exist. So remember what this means. Remember what it means for a limit to exist. The limit exists in this case if we travel to this point from the right side, and if we travel to this point from the left side. If they both point to the same place, then the limit does exist. So in this case, we can see the limit does exist. The limit of our function, sorry, not f of 1, I meant to write f of x. So if this, we can see that they both travel to the same point from both directions. We can say that even if the function doesn't exist at 2, the limit of the function does exist at 2, and it approaches 1. So the limit as x approaches 2 of f of x equals 1. The function doesn't exist at that point, but the limit of the function does. It's the important distinction to make. Let's say we have maybe a piecewise function. And this is just some generic function, nothing in particular. So we want to see if the limit of this function exists. I'm going to make this 1. I'm going to make this 1, and I'm going to make this 2. So we want to ask ourselves if the limit as x approaches 1 exists on this function. Does it exist or does it not exist? So a few things are going on here. Not only do we have this open circle right here, which indicates that there's no point there, but we have a little bit of distance up from that. We have a point, and then it continues the rest of the curve. So we want to take the same approach we did with the last limit problem to tell if the limit exists. So we want to travel to the point from the right side, and we want to travel to the same point from the left side and see if they convene in one location. And it doesn't look like they do. If we travel from the left, we get one limit value. If we travel from the right, we get a completely different limit value. So this one does not exist. So for functions, we say u is undefined. It's undefined if the function value doesn't exist. For a limit, we just say D and E. And that's just the technical definition we use when a limit exhibits behavior like this. We say that the limit does not exist. So there is something we can do to make it work, though. We're going to want to split it up into two one-sided limit. So at the moment, in the last problem we had, it was just one single limit, one two-sided limit. In this case, we're going to split this one up into two separate one-sided limits. So we're going to make one of them go from x to 1 from the left. So whenever we're traveling from the left, we use this little minus sign right there as notation. We say this is the limit as x approaches 1 from the left, or the limit as x approaches 1 from below. They're both acceptable. Same function, f of x. So we want to ask ourselves, theoretically, if x reached 1 from the left side, what value would we expect y to have? So we're going to start from here. We're going to work our way to the left, or sorry, we're going to work our way to the right from the left is what I meant to say. If we keep going until we hit 1, we can tell that we would expect the y value to be 1. So this limit would have a value of 1. Now we're going to do the same thing for the other side. We're going to have the limit as x approaches, this time it'll be 1 from the positive side. So we can say this is the limit as x approaches 1 from the right, or the limit as x approaches 1 from above. So we can see that if we start from the right, we work our way to the left, the y value we would expect to have at the very end of this part of the curve would be 2. So this limit would have a value of 2. So whenever we have a situation like this one, wherever we have one function, one x value, and if they happen to go to two different points, we say that this limit right here absolutely does not exist. They have to go to the same location for the limit to exist. So sure, this one doesn't exist, but these two do. Whenever we have a situation like that, we can always split it up into two separate one-sided limits to make this work in some capacity. We don't have one limit that works. We have two limits now that work from different sides. Let's talk about perhaps the most important reason why we even have to learn limits in this class. The concept of the derivative of a function. So we have all of these really nice rules we can use to quickly find derivatives of things. Power rule, quotient rule, product rule, chain rule, so on and so forth, but we didn't always have those things. Remember at the beginning of the class, we had to use what they call the limit definition of the integral to get, or I said integral, sorry, I meant to say derivative. We have to use the limit definition of the derivative to get our answer. So for example, remember that it's something like this. If f of x is some function, then the derivative of f of x, we call that f prime of x, that's the derivative, is equal to the limit as delta x, forgot the x, delta x approaches 0 of f of x plus delta x, I'll write the delta x in a bit, minus x all over delta x. This gives us the derivative of a function. So let's try an example of this. But before we do that, let's pick a function and then let's understand what's really going on. Because it's kind of hard to lose track of what this really means. In a lot of classes, they just kind of throw this at you without explaining why this is the way it is, where the limit comes from, where this stuff comes where it comes from. So it would do us a lot of good to review this. So I'm going to pick a generic function that works really well for this purpose. I'm going to use f of x is equal to x squared. We're going to find the derivative of x squared now using the limit definition. But first, what I want to do is I want to draw the function. That will help us have a really good graphical understanding of why this is the way it is. So that's our function. What is a derivative anyway? So we know that the derivative is just a rate of change. It is the slope of a particular curve at a particular value. So as we can see, it depends on what point we pick on the graph, as far as what the derivative is going to be. If we pick a point right here, we're going to have a tangent line right around there. So that only represents the rate of change of the function at that particular point. What if we picked one that's closer to the origin? What if we picked this point? Is it going to have the same rate of change? No, it certainly will not. This one is going to have a different rate of change. So as you guys can see, it definitely depends on where we pick the point to see what the rate of change is going to be. So we're going to talk about ways where we can get the exact rate of change at a particular point. We're going to call this right here, we're going to call this point A. We're going to call this one point B. So our goal is to find the derivative of point A. We want to find the rate of change of the curve at this particular value. We want to find the slope of the tangent line, but we don't know how to do that yet. So what we have to do instead is we're going to make a secant line. So a tangent line is a line that touches a curve only in one location. A secant line touches in two locations. So this goes through point A and point B, so this is a secant line. So what we're going to do is we're going to move B closer and closer and closer to A, and then see what happens to the secant line as we do so. I'm going to pick another point B, put that right there. I'm going to draw a new secant line. So that's the best I can do. So we can see that here, before we even talk about that, I want to do one more. So I'm going to pick another B, move it even closer to point A. So that's point B. The secant line is going to go right here. So as you guys can see, as B gets closer and closer and closer to A, the secant line gets closer and closer to what we expect the tangent line to be. So that's really what's going on in this limit. So what I want to do is I want to label different parts of the graph to help us have a conceptual understanding of why this is the derivative. So if we pick A and we pick B, A is going to have an x value right there. B is going to have an x value right there. So I'm going to call this, well, A is going to have an x value. I'm just going to call it x. So this distance right here is x. And then this distance right here, the distance between A and B, I'm going to call that delta x. Change in x between A and B. So what are the coordinates of point A? A is going to have coordinates x, comma, f of x. Easy enough, but then what about the value we pick for B? So this green B point right here, it's going to have coordinates. This would be, well, we know that A is x, so then B is going to have to be x plus delta x. And then what is the y coordinate? That's pretty easy. All we need to do is plug in x plus delta x into our function. So that would be not f of x, but f of x plus delta x. We have an x, and we have a y that depends on that x. So in this case, the y value depends on x plus delta x, in the same way in A as f of x depends on x. So we're taking the limit as delta x gets smaller and smaller and smaller. So we can see that delta x has a considerable distance. What we want to do now is we want to imagine that delta x is getting smaller and smaller. Eventually, we want to bring it small enough so that it's essentially zero. We're going to bring B closer and closer to point A until they eventually overlap. So what happens when A and B overlap? Well, they're going to be pointing at the same location. Not only that, but delta x will be effectively zero. There's going to be no discernible difference between the x value of point A and the x value of point B. Delta x will be zero. So that's why we use this limit. That's why it's important to understand what's happening here. We're taking the limit as the x distance between A and B gets smaller and smaller and smaller, and eventually becomes zero. Why do we want that, though? The reason why we want delta x to become zero is because that way we have a tangent line and not a secant line. We only have a tangent line if this part of the expression is true. Only if delta x reaches zero will we have a tangent line instead of a secant line. And then we know from algebra that slope is going to be change in y over change in x. So we already have change in x. Change in x between these 2 points we can see is that that's just going to be delta x. But then what about the change in y? So we're going to do y2, which is this one. That's y2 minus y1, which occurs right here. y1 is just f of x. So this whole thing I'm drawing in the box right now is y2. And this thing I'm drawing in the other box is y1. So our slope rules from Algebra 1 still hold in a calculus class. The concept of the slope has not changed even the slightest bit going from algebra into calculus. The slope is still exactly the way we think it is conceptually. And we still find the slope by doing y2 minus y1. And then this delta x is x2 minus x1. So a lot of people, I'm teaching the class for the 4th time now, and a lot of people don't understand why it's important to know what limits are for derivatives. And this is exactly the reason why. Because if we didn't have the chain rule and the quotient rule and all of those derivative rules, we would have to use only this to find the derivative. So let's quickly just use it to see if we can find the derivative of x squared. So we have the limit as delta x approaches 0. And then we're going to do f of x plus delta x. So what I want to do is I want to take this function, replace everywhere I see an x with an x plus delta x. So that means instead of x squared, we're going to have x plus delta x squared. So let's plug everything in. So we're going to have f of x plus delta x. Conveniently enough, we already know that's x plus delta x squared. Minus f of x, and we know f of x is just x squared, so we're going to subtract x squared. We're going to put all of that over delta x. So like I said before, limits can be really easy or they can be really hard. If we're given an algebraic limit, maybe something like this, 2x minus 3, we could do a direct substitution. All we need to do is simply plug in a 0 for x and we already have our answer. The problem is we can't do that with this particular limit we're given. When we're given the derivative of a function, we can't just do a direct substitution because we're going to have a 0 in the denominator. We can't have that. So what we're going to have to do is we're going to have to use some of our algebra rules to help us rewrite this so that we can do a substitution in the end. So we want to start by FOILing out this x plus delta x to the second. We're going to get x squared plus 2x delta x minus x squared all over delta x. So I see that we have an x squared at the front. I see that we have a negative x squared in the back. So what that means is they're both going to cancel each other out. They have a sum of just 0. So they both go away. We have 2x delta x over delta x now. So we're still going to be taking the limit as delta x approaches 0, but see that we have a delta x on top. We have a factor of delta x on the top. We also have a factor of delta x on the bottom. So it works really well because they both cancel each other out. So that means we no longer have any delta x. We only have 2x. And sure, we could have taken the derivative much easier using the power rule. We'll get the same answer. But now we have a really good review, a really good reminder of the conceptual reasons why it really is 2x. We have a logical reason we can always fall back on. So that's how we use a limit to find the derivative. Stop me at any time if you have any questions at all. So that's about it as far as limits are concerned. Let's get back into derivatives, shall we? So let's remind ourselves of the different derivative rules we've learned in this class. So I want to kind of give us something that employs all of them to a degree. And the quotient rule can get kind of ugly, so I think I'm going to have a separate problem to review the quotient rule. But for this one, let's try this one. So we have to determine exactly how to tackle this derivative. We're going to be using the chain rule, the quotient rule, the product rule, and the power rule. So what we want to do now is we want to see what's really going on, see if we have an inner function and an outer function situation. And to me, it kind of looks like we do. We have this big radical, and we have a bunch of stuff under the radical. So what we might want to do is change the radical into an alternate form. So instead of having this be a cubed root, I'm going to convert that into just everything under the radical to the 1/3 power. So we're going to want to use the power rule and the chain rule. So remember, the power rule works like this. We're going to take the 1/3, we're going to move it out to the front, and we're taking the derivative. Going to keep everything on the inside the same for now. And then we're going to take 1 away from the power. So 1/3 minus 1, that's 1/3 minus 3/3, we get negative 2/3. And then we're going to have to multiply everything by the derivative of the inner function. We're going to take the derivative of 2x, which is just 2. And then we're going to have to use the product rule to find the derivative of sine of x times cosine of x. So 2 plus the derivative of this product. So the product rule tells us we're going to do the derivative of the first times the second, plus the first times the derivative of the second. So we're going to do derivative of sine is cosine times cosine. So instead of writing that as cosine times cosine, I'm going to write that as cosine squared of x. And then we're going to do plus the first times the derivative of the second. So the first is sine of x. The derivative of the second is negative sine of x. So we can make that simpler just by making that negative sine squared of x. And then from there are some trig identities we can do to simplify that, but we're not really concerned with that at the moment. We're only meant to review calculus things during this section. So that's it. That's the derivative. Covers all the derivative rules. Let's review the quotient rule now. So I have a good example that would help demonstrate the quotient rule pretty well. Let's say we have a function. Let's say we have f of x is the tangent of x, and we want to take the derivative of tangent. And in order to do that, we want to write it as sine of x over cosine of x. So taking the derivative of tangent of x is the exact same thing as taking the derivative of sine of x over cosine of x. They are equivalent to each other. So let's use the quotient rule to take the derivative of this function. So the quotient rule tells us that whenever we want to do something like this, we're going to take the derivative of the top times the bottom. So the derivative of our top function, derivative of sine of x, would be cosine of x. We're going to have cosine of x times the bottom function. So cosine of x times cosine of x. Going to write that as the cosine squared of x. And then it's going to be minus the top times the derivative of the bottom. So the derivative of the bottom is negative sine of x. So what I'm going to do is I'm going to write this as negative sine squared of x. We have a negative there already. We're going to have another negative. All over the bottom squared. So our bottom function is cosine of x. We just want to square that. So this works out really nicely. We have two negative signs. A negative times a negative is a positive. We have sine squared plus cosine squared of x. And if you remember those trig identities we all had to learn in pre-calc, that is just equal to 1. We have a numerator of just 1. Denominator stays the same. But this thing kind of looks familiar too. If 1 over cosine of x is equal to secant of x, that means 1 over cosine of x is going to be secant squared of x. And in case you're ever wondering where they get these rules from, like if you're wondering why the derivative of tangent is secant squared, this is exactly why. They just did the quotient rule to get this result. So I think we have time to maybe cover one problem in implicit differentiation. So implicit differentiation is the process of taking a derivative implicitly. Up until this point, we've been strictly doing things explicitly. We've been taking the derivative of some function in terms of only x. So implicit differentiation is really useful when we're trying to take the derivative of a function that has multiple different variables in the same terms. So let me come up with an example. Let's try this. We have x times y plus 2x plus 3x squared equals 4. This is implicit differentiation. We want to take the derivative of y with respect to x. So if we had y equals blah, blah, blah in terms of x, things would be really easy for us, really simple, but they didn't give us something easy. We're going to have to use implicit differentiation for this. So remember, whenever we have something like that, we want to treat x, we want to take the derivatives of these things as we normally do. So we're going to do the product rule to take the derivative of x times y. That would be the derivative of the first times the second. So that would be derivative of x is just 1 times the second, which is just y, plus the first, which is x, times the derivative of the second. And derivative of y, we're going to call that dy dx. Derivative of y with respect to x. Derivative of 2x, that's simple. That just becomes a 2. Derivative of 3x squared, that just becomes 6x equals 4. So let's go ahead and solve for dy dx. So I want to move this and this and this to the other side. Excuse me. Going to subtract all three of these on both sides. So we get x times the derivative of y with respect to x equals 4 minus y minus 2 minus 6x. So that means all we have to do now is divide everything by x. So this x goes away, this x on top goes away, and we have our derivative. So our derivative of y with respect to x is 4. I guess we could simplify it. This would be 2 minus y minus 6x all over x. That is our derivative. That is how we do implicit differentiation. That's how we take the derivative of an implicit function in terms of two different variables. So that's it for today. Our other review session will be tomorrow at the same time, 6 to 6:30. So keep an eye out on the invitation. And as always, please come prepared with questions. If there's any particular problem you want to ask about, any particular concept you'd like to review. All right, have a wonderful evening. I'll see you guys tomorrow.